Hello, good evening. Welcome to today's live interactive session on geology and soil mechanics. I hope I'm audible. During this discussion, if you have any doubt, please feel free to ask. And even if there is any problem, like if you are not able to view anything on the screen or you are not able to hear me, so please feel free to interrupt me in between and raise the concern. So last 2 weeks, we already had the discussion regarding your week 1 lecture and the week 2 lecture. Okay. Uh, so the week 1 lecture was all about the index properties of the soil, right? So what are the basic properties of the soil and how you differentiate soils, one soil with respect to each other, and why do we actually need index properties? What are index properties? We studied all those things in the first week. And in the previous week, we actually studied or learned how, like, what are the different uh, methods available to classify a soil. Okay, so we learned about soil classification, and we also learned that why is soil classification actually needed, what is the need of soil classification. Okay, then we learned we saw that mainly there are three types of soil classification systems available. One is our Indian soil classification system, the other one is our uh, ASTO soil classification system, and as far as USCS soil classification system. Okay, so we mostly focused on the Indian soils classification system. We learned the various steps on how we can classify different types of soil based on the Indian standard soil classification system. Uh, we also learned the different types of soils that are possible, different namings, different nomenclature. How do you name them? And then after that, we solved some of the problems regarding this soil classification, right? So that was all about soil classification. And this week, actually, we are going to study about the soil compaction. Okay, so now gradually we are entering into the mechanics of the soil. So initially it was just starting the properties and the uh, how we name a soil and why is naming of a soil necessary. So we learned all those things, and now we are gradually entering to the mechanics of soil. Okay, the soil mechanics. So first thing which comes is the compaction. So what we will in this lecture we will like summarize whatever was taught to you in the week 3 lectures on soil compaction. So what is compaction? So what happens during compaction, and then we will be solving some of the problems from soil compaction. Uh, and after soil compaction, in the third week, the small introduction was also given regarding the soil permeability, right? That is how water flows through the soil. So regarding that also we will learn something. We will see what is that, and then we will solve some problems regarding compaction and also some basic problems regarding soil permeability. Okay, so let us start today's discussion. Okay, so why is soil compaction? Okay, so the first point of concern is, why do you need soil compaction? What is soil compaction? So compaction, I think The literal meaning of compaction is quite clear, that compaction nothing means to to what? To densify something, right? Compaction literally means to densify, right? To compact, like to apply force from all direction and to reduce it in size or reduce something in its volume. Okay, that is the literal meaning of compaction, right? Now, what is the basic main purpose of soil compaction? So the main purpose of soil compaction is to densify the loose soil. Okay, so that is the main target of soil compaction, right? So main target of soil compaction is to densify loose soil. Okay, then why do you need compaction? Why do you need to densify loose soil? The reason is because, see, in construction of highways, okay, highways, or you need to prepare the subgrade first, above which the highway is to be constructed. Okay, or you need to construction embankment. So due to so you need to construction some embankment. So for constructing some embankment, some certain criteria are there. Okay, criteria such as the density of soil in the embankment that you should maintain. Okay, the certain density you should maintain, right? That is the main criteria. Now, in order to maintain that density, you need to uh, put some amount of water in it. Okay, you need to mix some amount of water in the soil so that you can densify the soil in the while construction of the embankment, right? So this compaction theory, or this chapter will help us. Okay, this chapter will actually help us in calculating the amount of soil that we need to borrow from someplace else to construct our embankment or our engineering structure, fulfilling certain criteria. Okay, those criteria might be the criteria of the density. Okay, density, volume, anything. Okay, so we will be learning certain concepts using which we will be able to actually calculate, okay, numerically calculate how much water we need to mix, how many passes of roller. Okay, so for compaction, generally in the field, what we use rollers, right? We have seen some big vehicles which have drum-like things as their wheels. So those things actually compact, okay, densify the soil, and and for that thing we actually need for densify the soil, right? So we have one target density which we need to achieve. So to achieve that target density, we need to the roller actually needs to have certain fixed number of passes. Okay, if the roller passes over that soil too many times, then the soil will be more dense. Okay, more dense. And if it is less, if passes less, then it will be less dense. That in both these cases, our criteria of the density won't be satisfied. So we need to determine the number of passes of the roller. So how can we do that? We will be learning from this chapter actually, right? So let us see what is compaction. So compaction is nothing but densification of soil by removal of air. So this is very important. Okay, so how are you densifying the soil? Remember that compaction, the term compaction refers to densification by removal of air. Sorry, and nothing else. Okay, only layer. You are reducing the, we are compacting, you are densifying the soil mass by removing air. Okay, nothing else, not water or something else. Just by removal of air, you are what you are doing is you are densifying the soil, right? So this is known as compaction. Okay, so in order to remove air, you need to apply some external mechanical energy, right? So this process needs some mechanical energy. So how to provide that mechanical energy? That is with the help of a roller, right? Road roller in the field, correct? So compaction is nothing but densification of soil by removal of air. Now to aid compaction, what we need to do is we need to add some water. So what does water do? Okay, so water is actually added. So what does water do? Water actually helps in the lubrication of the soil particles. Okay, what happens due to water? That water is just a lubricant. What is lubricant? Lubricant is something which reduces the friction between two particles. Okay, this reduces the friction between particles. So what happens is water acts as a lubricant. So we add water. After adding water, we allow our roller to pass. So what happens is that due to the lubrication of the water, the friction between the particles reduces. So they are more easily they are able to slide amongst each other, and they are able to obtain a compacted or densified state. Right? Right? So this water actually help as a lubricant. But see, if you keep on adding water infinitely, you just keep on adding water, you keep on adding, what will happen? Intuitively, what does come means what thing comes to our mind? What will happen if we just uh, keep on adding water? The thing which is going to happen is that the uh, Vasudeva, please can you mute yourself?
The flow of the soil, sir. If
Yeah,
you are adding more water, the
yeah,
soil will be leakage through the water.
yeah, exactly. So what will happen is that soil
Liquid.
will be totally in liquid state, right? It will be watery. It will be in a watery state. So we need to add water up to certain limitation. Okay. So there should be a certain maximum point up to which there is water. So what happens is that, so this way, if I plot the water content, and in this direction, in the y-axis, if I plot the density, so what happens is that as you keep on increasing the water, the density keeps on increasing, right? The density keeps on increasing, the soil keeps on attending a more denser state,
Yes, sir.
right?
Yes, sir.
The soil keeps on attending a more denser state. But what happens is that after a certain point, after a certain maximum point, what happens? The density keeps on reducing. This happens because the water particles actually continue replacing the soil particles. Say you have a certain volume, okay, this is the fixed volume. In this volume you have some soil particles like this. So initially what will happen is that when you start adding water, the soil particles will get densified. Okay, in this volume the soil particles will be densified. But after a certain point, what happens is that these soil particles will be replaced by water. Okay. Okay. So as a result of this, what will happen is that the dry unit weight will reduce, because the weight of my dry weight or the weight of the solids will keep on reducing because it has been replaced by water. So what happens? Our density comes down. So there is a maximum density that you achieve. It is actually the MDD, or maximum dry density, and this is achieved at a particular water content which is known as the optimum moisture content. Okay. Okay, so here I have written the same thing, that uh, the water content at which the maximum dry unit weight is obtained is called the optimum moisture content, right? So sorry, so this is my dry density, this is my water content. So I obtain a certain bell curve like this. So this point at which there is maximum dry density, that is known as the this is the maximum dry density point, and this water content is known as the optimum moisture content, right?
Yes, sir.
So how do we determine the optimum moisture content? It is determined by the standard proctor test. Okay. Though these tests we generally perform in the lab, or we can perform it anywhere. So not it's not, the setup is not that big or that expensive. We need some mold, there is one mold of a certain volume and size. We need that mold, and we need a rammer. Okay, rammer using which we can compact the soil. So we need these two things, and using these two things, what we can do is we can do the proctor test. So so let us see the proctor test now. So how the proctor test is generally done. So this is the apparatus which I was talking about. Okay, so uh, this is the apparatus, right? So the proctor apparatus consists of a mold. Okay, so this is the mold, and this is a rammer. Okay, rammer. This rammer is actually used to compact the uh, compact the soil. Okay, the volume of the mold is fixed in, see, there is one standard proctor test and one is one modified proctor test. Okay, there are two proctor tests, and also there is one Indian standard. Okay, so this is a see that these are the parameters of the standard proctor test. So the volume of this mold is fixed at 944 cc. The diameter of this mold is fixed as 100.1.6 mm. Okay, so what we need to do is you need to give certain number of blows. So what we do is we take some amount of soil. Okay, some amount of soil, and that amount of soil we need to fill in this mold in three layers. Okay, three layers. So what we do is we put one layer of soil, and then we put 25 blows on that soil. Okay, and that gets compacted, and after that what we do is we put another layer of soil. Again we put 25 blows over it, and again we put a third layer, and again we put 25 blows over it. Okay, so like this we fill the mold, and the top portion is actually trimmed off. Later it's trimmed. So the weight of the hammer is also specified. It is 2.5 kgs, the weight of this, and the free fall of this hammer, the free fall from here to here, it's actually 30.5 centimeters. Okay, so these are the specifications of the standard proctor test, right? So one second. Yeah, standard proctor test. But now I want to tell one more thing here, that there is one modified proctor test also. Okay, so in that modified proctor test, or uh, it is actually like what happens is that the number of layers are actually increased. Okay, number of layers are increased, and there is one Indian light compaction test which is similar to standard proctor test, but these dimensions actually very little bit. Okay, so I will suggest you that you please look into the IS code. If you just Google it, you will get that. Just IS code on proctor test or compaction test, you will get all the details there. So Indian standard, this Indian light compaction test had some specification which are little different than the standard proctor, almost same. Like the volume is in the Indian test is 1000 cc. Okay, in the standard proctor test is 944 cc. So little bit changes there, but almost similar to standard proctor test. Okay, and the modified or the and the modified proctor test and the Indian heavy compaction test, those two are similar. So what we do is that we first we find the moist unit weight from the volume of the mold and the weight of the cell. So we know the weight of the mold. Okay, then you know the volume of the mold, correct? Or now you have filled the mold with certain amount of soil, and then we can again take the weight. So you know the weight of the mold plus the soil. Now if we deduct this weight from this weight, we will get the weight of the soil, correct? We get the weight of the soil, moist soil. Okay, now from the moist unit, so we can find out the gamma moist unit weight from this weight, W moist divided by the volume of the mold. If you do this thing, we can easily find the moist unit weight of the soil. Okay, now from this moist unit weight, how can we calculate the dry unit weight? Okay, how can you calculate the dry unit weight? So we had used this formula many times. What is gamma dry? Is nothing but gamma moist by 1 plus water content, right? Water content. So if we know the water content, we can easily find the dry density, right? So what we do is that, right? So what we do is that we uh, so we uh, in the mold, what we do is we fill the soil in 3 layers, right? Fill the soil, take the weight, find out the weight of the moist soil. Now what we do is we take little amount of soil from there, and like to the find out the water content by putting in the, like this is a basic test, right? Finding out the water content of the soil, which we can easily find out by using the drying the soil in the oven. So we dry little amount of soil in the oven and find out the water content. So for each soil, we will know the moist unit weight, and we will also know the water content, and from there you can find the dry unit weight. Okay, so for each field we can know the dry unit weight, correct? Now what you can do is you can add some more water again into the original soil sample, add some more water, mix the soil properly, and again we can fill the mold in 3 layers. Okay, then again we can uh, so what we are doing is actually we are increasing the water content little by little and doing the same, repeating the experiment. Okay, so by doing this, what we will get, we will get a series of data where we will have the moist densities, water content, and moist densities, and then you can calculate the dry density from the water content. Okay, so you'll get a series of data. Okay, this will, and using those data, what we do is that we plot the dry density versus the moisture content curve. Okay, so here, see, here we have that from a for a given moisture content and degree of saturation, the dry unit weight can be represented as gamma dry is equal to G into gamma W, G into gamma W by 1 plus E. So this we already know this thing, where what is our what so we know another thing, that SC is equal to W into GS. So if we replace this E here, we can write that gamma T is equal to GS gamma W by 1 plus WGS by S. Okay, so this is also one important relation we can get, where for a particular uh, state of saturation, we can find out the dry density of the soil, right? And now, so you might be thinking, why are we using this dry density, right? So the only reason is that if we remember from our first week lecture, the dry density is nothing but density is used as a measure of the denseness of the soil, right? Direct measure of the denseness of the soil. So we are here determining the dry density. Just a second. Yeah. So for a full compaction, there should not be any void present. That is, the air void should be 0. So this is a very ideal case. So in the theoretical case, it is very ideal case where so you have compacted a certain amount of soil, and during that process of compaction, you have applied some mechanical energy, and you have applied that mechanical energy so well that there are no voids present in the soil. You have totally eliminated the amount of voids present in the soil, right? So remember that for 100% compaction, the air void should be 0. But practically, is this possible?
No, sir.
No, it's not possible, right? Practically, this won't be possible. Okay, it's not possible that we will be able to eliminate that. No experimental procedure is that much potent, then it can eliminate 100% of the air voids. Okay, so in the case where you are able to achieve full compaction, means you are able to eliminate, in the case where you are able to eliminate all the voids, in that case only soil solids and water would be present. So see, let us see here. So we have our soil solids, we have our water, we have air. Okay, so in the like, what to say, most like in the ideal case, what you have done, you have eliminated this air completely. Okay, so this is not there. So only there is soil and water in your system, right? So the air was see, so this much volume is totally expelled. Okay, this much what you are doing is that this much you are totally airwards, you are totally taking out of your soil. So what happens is that the volume reduces. Volume was initially this much, so it will reduce to this much. Okay, it will reduce to this much. So in this part, if you see in this volume, so it is V. In this volume, my soil, I can call my soil that it's say like all like completely saturated, right? In this volume, my soil behaves as if like seems that as if it's 100% saturated. It is S equal to 1. So the maximum dry unit weight that is theoretically possible at a given water content is when there are zero air birds, and when there are zero air birds, it is when my this saturation is equal to 1. Because in this volume there is, see, this is the reduced volume, right? In this reduced volume there is only soil and water, so I can say that my soil is saturated in this volume. Remember, I'm talking about only this volume. Okay, so this is the relation. This is the relation that we studied, this relation that we saw in the previous slide. So if I put s equal to 1 here, s equal to 1 here, the density that I will get is known as the zero air void dry density, right? So there are no air. So this is a only theoretically possible. Practically, this is not possible, right? So we know the G value, you know gamma, you know water content. Okay, so we can have a line. We can draw a constant line. So you have the water content here, and you have the gamma. So actually, you can get a line like this. Okay, which is known as the zero air void line. So this is the theoretically maximum possible value of dry density that you can achieve at a particular water content. So at this water content, this is the maximum value of dry density that I can achieve. Okay. So this is the theoretical maximum of a water content that I can achieve. Remember that practically it's not possible to achieve this. Okay.
Okay.
So if we look into this curve, so this is our right. This is a curve. Okay, bell curve. This is the moisture content this side. This is my dry unit weight this side, and this is my zero air weight. Okay, so this zero air weight line will never touch my this bell curve. This is because practically is impossible to achieve that dry density. Okay, practically see, for this water content, this is my dry density which we obtained, maximum dry density which is little above 18, right? This is the dry density that we obtained for our optimum moisture content, maximum dry density. But theoretically, the dry density that you can obtain is much higher. It will be here something. Okay. Theoretical maximum is this one, but practically only up to this much only we can obtain. Right? Then actually we have what are the factors that affect our soil compaction, right? So the main factors that affect the soil compaction are our first is the soil type. Okay, soil type means the grain size distribution. Okay, in case of coarse soils, the grain size distribution is the main thing which determines the uh, degree, like determines how much you can compact a soil, right? Then in case of our fine grained soil, it is nothing but the uh, type of clay mineral present. Okay, type of clay mineral that will determine. Okay, because see, also type of clay mineral, also how is the structure of the soil particles. See, either they're flocculated, either they're dispersed. So all these things will actually affect the compaction. Okay, and the second most important thing is the effect of compactive effort. That means how much force, how much mechanical energy you are putting yourself to compact this soil, right? So we need to put some mechanical effort in order to compact the soil, right? We need to put some external mechanical energy. So how much compactive effort actually we have to put in order to uh, uh, compact, so that will actually determine the degree of compaction. So say this is my moisture content versus density curves. Okay, so if my if this is the curve obtained from the standard Proctor test, okay, then what will happen for from the heavy Proctor test, my curve will actually shift like this. So what happens is that the moisture content reduces, optimum moisture content for the same soil. I'm speaking of the same soil. For the same soil, the moisture content will reduce and your dry density will actually be higher. Okay, so this is for heavy compaction. So so if you increase the amount of energy that you are putting in, so what will happen is that the optimum moisture content will reduce and the dry density will go up. Okay. Okay. So like this, say we keep on plotting certain graphs, so you keep on increasing the compactive effort. So these are all the optimum points, so if you join all these points, this is actually known as the line of optimums. Okay, but still, however, how much energy you put in, you cannot touch the zero air void line. Okay, obviously, say you can get very close to it, but you can never touch the zero air. Okay, so here now I have written about the modified Proctor test. Okay, that I was speaking about. So modified Proctor test means a little higher energy you are putting in. Okay, so modification of the standard Proctor test to represent field conditions in a better way. So the standard condition. So in order to represent the field conditions in a better way, this modified Proctor test was introduced. So if you see the main difference between the standard Proctor test and the modified Proctor test is here. Is in the number of layers, the height of fall, and the hammer weight. So these three things are actually differing. So what is happening here is that there are 5 layers. Okay, the size of mold is the same. Okay, in that same volume, what you are doing is you are putting more amount of soil. How you are putting more amount of soil? You are first how you are putting by 2 ways. The main thing using which you're occupying more soil into that same volume is that you are using the weight higher energy, right? A weight a hammer of higher weight, and also you have increased the height of free fall. Okay, before it was around 30 centimeter and 2.5 kgs. Now you increase the weight of hammer to 4.5 kgs and the height of fall to 40 more than 40 centimeters. So due to that, during the compaction, when you will compact the layers, what you are doing is that you are putting more energy per layer. So what will happen is that you can put more amount of soil in that same volume. Okay, so this is the modified Proctor test. So these three things means in the standard Proctor test there were 3 layers. In the modified Proctor test there are 5 layers, right? So hammer weight has also increased, the height of fall has also increased. So if this is the graph for my standard Proctor test, then my modified Proctor test will somewhat look like this. It will be shifting towards the left and up. So this is very intuitive, right? So obviously, if you are putting more energy, less amount of water will be required, means less amount of lubricant will be required. So that is why this optimum moisture content is reducing, coming towards the left as you increase the compactive effort. Now field compaction. How is compaction actually done in the field? So in field, see, we cannot ram, right? The area is huge, vast. Embankment you can consider, right? Road embankment. So it's huge. The length is kilometers, okay. Many kilometers. So obviously it is not possible to ram using rammers, okay. Big, however big, you cannot ram it, right? It's practically impossible. So what we need to do is that we need to use rollers, okay. So there are many types of rollers. So the first kind of roller is our smooth wheeled rollers, okay, or smooth drum rollers, okay. These are very common types of roller which are seen from villages to cities, from everywhere. This kind of roller can be seen. When in village road construction also, small road construction also, these kinds of rollers are seen. So these rollers are nothing but they are like very they have smooth wheels. So the wheels are actually like the cylindrical, right? Cylindrical wheels, front and back. So that's why they are known as smooth wheel rollers, okay. So when are the smooth wheel rollers used? So these are suitable for rolling subgrids, okay. Subgrid is, you know, the layers of the road, right? So there is subgrid. Above the subgrid there are many other layers, and above that where you place the bitumen, okay, the bitumen of the road. So subgrid is the layer which forms the basic structure of the road that we form. The pavement that is formed by a flexible pavement is formed by the subgrid. The subgrid, it is used to roll the subgrid. Okay, so in the embankment, roll the initial soil. We used a smooth wheel roller. Okay, so these are actually used for finishing up. So as the wheels are very smooth, so it gives a plain smooth finish of the soil. So these are mainly used for giving a smooth finish to the soil, and both kinds of soil it can be used, both clay and sandy. Then we have the pneumatic rubber tired rollers, okay. So in these pneumatic rubber tired rollers, so there is a kneading action. So kneading means it was very nicely explained by mm, uh, the course instructor during the lecture. The kneading means what we do. Kneading, if you want to imagine it, we need flour, right? Flour, atta or maida, we need that, right? We put some water and then make the dough. So that process is called kneading. So these pneumatic rubber tire rollers are actually, they provide a kneading action. So due to this kneading action, the compaction is like far more superior. The compaction achieved is far more superior than our smooth wheel rollers, right? But the main difference is that in smooth wheel rollers, see, it is completely plain, right? The base is completely plain, so there is 100%, say 100% coverage of the cover is 100%. But in pneumatic rubber tire rollers, the cover is only 70 to 80%, because see, in pneumatic rollers, the wheel is not like this smooth. So there are some parts, okay, it's like small parts, round parts, some parts that together form a complete wheel. So the coverage is not 100%. Then we have the shift foot roller. So these kind of rollers, they have a drum, and in drum there are certain projections in this drum. Okay, so these projections actually help mainly in compacting our clay soils. Okay, shift foot rollers are mainly used to compact clay soils. These are very helpful in compaction of clay soils. So if anyone asks you what kind of roller you have to choose, if the soil in the site is clay, then your answer should be shift foot roller. Then we have vibratory roller. Vibratory roller. So intuitively, you can say that it should be used for sandy soils, right? So say if you have a sand in a container, okay, you fill the sand in a container. So what if you if you give some vibration, if you move the container like this, give some vibration, whatever, the sand will settle down and achieve a more denser configuration, right? So the same concept, what happens, the vibratory rollers are used. Those are mostly used to compact sandy soils. Okay, so they are very efficient in case of sandy soils. Now specifications for field compaction. Okay, so in field generally it is told that, see, in lab by the Proctor test, you can achieve certain amount of compaction, right? So certain amount of dry density for a particular amount of soil you can achieve. Okay. But so first you do the experiment in the lab, and then when you have to translate this same dry density in the field, say I need to construct the embankment using this same soil in the field, what I need to do is I need to instruct the site engineers that this much amount of dry density you need to achieve. So that dry density is generally 90 to 95% of the maximum dry density that is determined in the lab. Okay. So so what I was telling is that this 90 to 95%, so you do the Proctor test in the lab. Okay, after doing the Proctor test, you determine the maximum dry density. Now you need to, for that soil, the soil that you have tested and done the Proctor test in the lab, for that same soil you need to compact in the field. So you need to instruct the site engineers in the field that this much compaction you need to achieve. So what we tell the site engineer is that you achieve 90 to 95%, like you give the certain value of dry density, you tell the site instructor that you need to achieve this much dry density in the field. And that dry density that you need to achieve in the field, it is generally 90 to 95% of the dry density, maximum dry density that you obtain in the lab. Okay, so from here we get another term which comes relative compaction. So the relative compaction is nothing but the dry density in the field divided by the dry density in the maximum dry density in the lab into 100%. So this is my relative compaction. So if someone tells me that relative compaction is 100%, that will mean that in the field also maximum dry density has been achieved. Okay, whatever was achieved in the lab. So for granular soil, the amount of compaction is generally represented in the terms of relative density, right? So generally, relative density is used to specify the amount of compaction that is needed for a granular soil. This is for sandy or gravelly kind of soil. So can you tell me what was the uh, relation, or how do you determine, what is the formula for relative density? If you remember.
E max minus E natural divided by E max minus E minimum.
So,
and 100%.
So this relative density term is actually used to determine the specify the amount of compaction that we generally amount of compaction which is needed to be achieved for a granular soil, right? So if the relative density is high, means it is very nicely packed, like very densely packed. If it is low, that is the compaction is not proper. Now, how to determine field unit weight? Okay, so see, so here we need this field unit weight. We are writing everywhere. So how will we actually determine this field unit weight? Okay, you do certain number of passes and everything of the roller, and then you construct the embankment. Now, how will you check that what is your field unit weight? So to determine the field unit weight, so there are many methods. Okay, so out of these methods, the main method which we will be focusing is the sand cone method. Okay, sand cone method or the sand replacing method. The sand cone method is actually specified by American standards. Okay, A.S.R. And a similar method is there, which is known as the sand replacement method, that has been specified in our Indian standards. Okay. So what is the sand cone method? So a sand cone method, in the sand cone method, we have a plastic jar. Okay, it is a device, a sand cone device is there, which consists of a glass or plastic jar with a cone attached to it. Okay, there is a metal cone attached to the. So this sand cone method is actually given by this ASTM code, ASTM D1556. So what we do is that we go to in the field, we use this instrument, this apparatus to determine the field density. Okay, so we know, so what we do is that in this jar we feel certain amount of sand, so we completely fill up to here. We'll fill this jar with sand. Okay, then we take the weight first. So we have the weight of the jar plus this weight of this cone plus weight of the sand. Okay, which is W1, it representing as W. Then what we do is that in the field, say this is the top view. Okay, so in the field in we make a small hole like this diameter size. Okay, this size, we make a small hole and we excavate that hole. Okay, and from this hole, actually when we excavate, the soil will come out. So what you happen, you collect that amount of soil. You collect that amount of soil and we weigh that soil. So that weight is actually W2. Okay, that is the weight of the excavated soil from that hole. This W2. Now, this excavated soil, you can measure the water content in the lab. Okay, you can put it in the oven and measure the water content, and that is known as, that is W. Okay, okay. So if we know this water content and we know this W2, you can get the dry weight of the soil. So dry weight is nothing but W3 is equal to W2 by 1 plus W. Okay, water content. Okay, so using this relation, we can find out the dry weight of the soil. Now, what is done is that this, if you remember, so this is completely filled with sand, right? So what we do is that so this is completely filled with, so what we do is that we completely invert this cone over that hole, and we open the valve here. So as soon as we open it, so all the sand will come out, right? And then we close it. Okay, we open and close it. So certain amount of sand has come out. So how much amount of sand will come out, if you can tell me?
Depending on the hole in the cone.
Yeah,
Size.
depending on the size,
Hole.
size of the hole in the, that hole that we have made in the ground, depending on that, and also the this cone, right? Size of the cone. Okay, that much amount of soil will also come out, right?
Yes,
Then
sir.
what we do is that we take the take the weight. Okay, so this should be one second. W4, huh? Should be W4. So we take this weight. So again, so some amount of sand has come out from the jar. So then again we weigh this. So we now get the weight of the remaining amount of sand plus this jar plus this cone weight. So we get W4. From, so how much amount of sand will actually has actually filled the cone and the hole in the ground? How can we find that out? If we deduct from this W1, if we deduct W4, we can get the amount of sand that has filled our hole and also this cone. Okay, if we deduct that, we can find this weight W5. Right now, from that W5, if we deduct the weight of the soil only in this cone, okay, only in this cone, a certain amount of weight of the soil it can hold, right? So if you deduct that soil, that weight, this is the weight that will be obtained, W5 minus W6. So ultimately what we are doing is, ultimately we are finding the weight of the soil in the weight of the soil, that is weight of the sand that has filled the hole in the ground. So that weight divided by the dry unit weight of the sand. So you need to know the dry unit of the sand which you are using in this experiment. So if we divide this, we can get the volume of the hole, right? So now you know the weight, you know the volume. So use now actually you've determined the density. So now you know the volume, right? You know the volume, and now also you know the dry, this one, the dry weight of the soil. Now this dry weight of the soil, W3, divided by this volume will actually give you the in situ, dry density of the soil in the field condition. Okay, so this is actually very difficult to explain like this. It's very simple experiment in the lab. It is very simple experiment. You can easily do it. It's actually very easy. Okay, in the lab it's also very easy to explain. So I suggest that you watch this video. Okay, in this video actually properly everything is given, how to determine the this one, uh, unit weight of the dry unit weight of the soil in the field using this method. Okay. Then many other videos are available. Also, please watch the sand replacement technique video that is there in YouTube. That is by NCTL. I forgot. It is by National Teachers Training Institute, I think. Some videos are there. So they have explained very nicely how to determine the in situ unit weight of the soil by using sand replacement technique. Okay, I suggest you watch those videos in YouTube. Now, one more thing, one more. So this is actually nothing. This ends our compaction. Then this compaction is a very short and simple chapter. Nothing much is there. So it's very easy. So this was all about compaction. Okay. So we will solve some problems in compaction after we finish this part. Okay. So one more topic that was discussed in the third week was permeability. Right. So what is permeability? So water flows. So if we have certain amount of soil and certain amount of soil, and that soil actually allows water to flow through it, right? So that property of the soil or any other substance, okay, it may be anything which allows a fluid or a liquid or anything, maybe gas also, to flow through it is known as permeability. Okay, so how does actually water flow in the soil? So as you know, in the soil, there are the soil grains and there is also some void, right? So water actually travels through the void. So these voids actually form a network. Those voids, all the voids in the soil, they form an interconnected network. And that interconnected network, like you can imagine as a interconnected network of pipelines, right? So that interconnected network of voids actually allows the flow of water through a soil mass. Okay. So water flows through soil due to the presence of interconnected voids. Now, flow always occurs from the point with high head to lower head. Obviously, water will always flow from a point of higher energy to a point of lower energy, right? So that is very obvious. So head is the term that we use here. The flow occurs from the point with higher head, means higher energy, to a point of lower head, that is lower energy. So, and during this flow, when water flows from a higher position to a lower position, some head loss occurs, right? So in this process, there's some head loss occurs. Okay. So say this is a soil mass, right? So this is my data. Okay. So this is my point A point. So the head here is HA, the head here is HB. Okay. So this is my soil. So water actually flows from this point to this point. And in this process, there is some head loss. Head loss means loss of head. So at this point, the head is higher head, and this point the head is low, it is lower head. And so the water will flow. And during this flow of water, there is some head loss. So what is the head loss? Head loss is nothing but HA minus HB, which is the head loss. So there is some loss of head, and the water is flowing along a length L, right? So what is my hydraulic gradient? Hydraulic gradient is nothing but I is equal to this delta H, means the head loss divided by the length of flow. Okay, so this is my hydraulic gradient, right? Now let us come to Darcy's. So Darcy's law, what Darcy's law says is that the velocity of flow of the velocity of flow of water is actually proportional to this hydraulic gradient. Okay, so while water flows from a higher head to lower head, while water flows from a higher head to lower head, there is some head loss. Okay, so due to this head loss, there is some hydraulic gradient, which is given by del H by the length. So as water flows along this length, there is some velocity of water, right? So this velocity of water is actually proportional to the hydraulic gradient. Okay, this is given by Darcy. Now the main thing to note here is that this this relation is only valid for laminar flow. That is the when the flow is laminar. So can you tell me what is meant by laminar flow, if you have any idea?
Laminar flow, I think the flow will be less medium. Oh, not a high level flow of water.
Yeah, means laminar flow actually means is that when when water flows, okay, so water is flowing, right? So laminar water or any liquid is flowing. So laminar flow is that all there is no like intermingling of the layers of the liquid of the flow. All the layers are flowing with their own, like they are discretely they are flowing. There is no intermixing of layers. So the opposite of laminar is actually turbulent, right?
Yes, sir.
Turbulent. So there is no intermixing of layers. So all the layers are discretely, all the layers of water are discretely flowing. That is actually laminar flow. So Darcy's law is only valid when the flow is laminar. So if I plot my hydraulic gradient to the velocity v, so my graph is actually like this. So if you see only this part, it's linear. So in this part, it's laminar. So Darcy's law is not valid here. Okay, it's only valid in the laminar region, where in the only in the laminar region, my velocity will be proportional to the hydraulic gradient. And we can reasonably assume that the void spaces are very small, right? So as the void spaces are very small, the water will be in laminar because the velocity is very slow, right? So the water will be in laminar condition. But in case of rocks where there are huge fractures, okay, fractures, in that case actually Darcy law is not might not be valid because there might be turbulent flow through those cracks. So here V is nothing but the V is called the discharge velocity. Okay, and this is my hydraulic gradient. Now one more very important term which comes is the seepage velocity. Okay, so what is seepage velocity? Before that, see, V is proportional to I, so we can write V is equal to Ki. Okay, so K is nothing but the constant, right? K is a constant, and K is called the coefficient of permeability. Okay, K is so. Can you tell me the unit of the coefficient of permeability?
Sir, I don't know, sir.
No, tell from the expression, na. Tell from this expression. K is what? K is equal to V by I, right?
Yes.
K, sorry. Yeah, K is equal to V by I. So what is the unit of velocity?
One.
What is the unit of velocity? Meter per second, right? Meter per second or centimeter per second, right?
Yes.
Right. And what is the unit of hydraulic gradient?
It's also same. Same.
Hydraulic gradient doesn't have any unit, right? So length by length,
Okay.
unitless, it's a gradient. So what will be the unit of my coefficient of permeability? Centimeter per second or meter per second only, same as that of the velocity.
Okay.
Correct. So it is the same unit. So it's generally represented in terms of centimeter per second. Okay, that is the unit of permeability. Okay, one more thing I remember from the last lecture actually, there I in the video in the uploaded video in the YouTube I have actually mentioned in the comments also I've corrected it. So there was one question I told that it should be SCSM, so actually it should be SMSC. Okay, SMSC, that's all. one question was asked in during the class. At that time, I told that it's SCSM, so it should be SMSC, I think. So I have actually meant, if you open YouTube and see the comments of the comment in the comment, I have pinned, I have mentioned the timestamp, and I have actually given that correction there. The last week's video. Okay. So just a second. Just a second. Yeah. So so the coefficient of permeability is the nothing but the proportionality constant, right? So the different types of soils have different types of coefficient of permeability. So it's a material property of the soil, right? So different types of soil will actually have different values of coefficient of permeability. Next, we come to the seepage wells, right? So see, if we consider our soil as a pipe, so some amount is filled by the soil solids, okay, and other part is filled by the voids, correct? Correct. So some part is filled by the voids and some part is filled by the solids, okay. Now let us assume that VV is our volume of voids, okay, and VS is the volume of solids, okay. Now what is the total flow? What is the total, what is the formula for flow? Velocity, flow is nothing but the velocity, flow or discharge is represented by Q, okay. Okay, it's the volume of water flowing per second, right? So what is the expression for the flow? This is flow. Expression for flow or discharge is nothing but velocity into area, okay. The velocity of flow into the cross-sectional area. So if this is the cross-sectional area of our pipe, which is A, so the flow and the velocity of flow is V through this pipe. So the flow through this pipe will be nothing but the velocity of flow into the area of cross section of this pipe. This is A. Okay, Q is equal to V into area of cross section. Right now, this area is actually formed by my area of voids plus by my area of soil solids, right? So the area of soil solid, area of voids plus the area of soil solids. So this is the total, these are the constituents of my area, right? Now, actually, if you see the flow that is occurring, that flow is actually occurring through what? Is it occurring through the total area? Yes. Is it occurring through this total area? No, right? My flow is actually occurring only through the voids. Yes or no?
Yes, sir.
My flow is not occurring through this part, through this solids part. My flow is actually my actual flow is occurring only through the voids, right? So I can equate this with velocity through the voids, which is represented by Vs into the area void zone, because my actual flow is actually occurring through only the voids, right? Not through the soil solids, but we're taking the total area you're taking, but this is actually not true, right? We're averaging the area or taking the total area, but the actual flow that is occurring, that is only occurring through the voids, okay. Okay, and the flow of water, if we consider the flow only through the voids, that is known as the this Vs, that is the superficial velocity, okay. Superficial velocity is the velocity of water that that velocity of water when we consider that the flow is only occurring through the voids only. Okay, not through the whole area, but only through the voids. That is the reality in reality what's happening, right? Only through the voids. Okay. Now, now see. Now what we can do is that we can write it like this: Vs equal to V into AV plus AS by AV, right? Just we are rearranging. Then what we do is that we multiply length in the top and in the bottom. Is the length of flow. Say we are assuming this is a pipe, right? So length of flow, the length of the pipe we are multiplying L. So L, as soon as we multiply L, we will get the volume. We will get the volume of voids plus volume of solids by volume of voids. Correct?
Yes, sir.
Now, see, now if we write it, volume is equal to V into 1 plus Vs by Vv, right? You can write this or not,
Yes, sir.
right? So what is Vs by Vv? What is
Volume,
volume of solids by volume of voids? What is
yeah,
that?
flow.
No, no, no. In terms of index property, think in terms of index property. Tell me what is void ratio, E? What is void ratio? Void ratio is volume of voids by volume of solids,
Yes, sir.
isn't it? So
Yes,
what
sir.
is this term? So, so this term is nothing but 1 by E, right? So we have Vs equal to V into 1 plus E by E, right? And
Yes, sir.
this term, if you remember, it is nothing but 1 by N. So Vs is nothing but V by N. Okay. And where N is my volume of voids by total volume of nothing but porosity. Okay.
Okay.
So now tell me from this expression, can you tell me which will be greater? Vs is greater or V is greater? Which is true? Vs is greater than V or V is greater than Vs?
V is greater than Vs, sir.
Why?
Volume of solid is less than total volume.
Hmm? See, what is the value of porosity?
Value of
Value of porosity will always be less than 1, right?
yes, sir.
Will always be 1 or less than 1. Generally, it will be less than 1. If there are voids, that means volume of porosity will be less than 1. Yes or no?
Yes, sir.
So 1 divided by something which is less than 1. Obviously, this will be some Vs into 1 by N into V. Okay, that means what? V is equal to N into Vs. Okay, so this porosity is always less than 1, right?
Yes, sir.
So V will be always be less than Vs. So Vs is actually, so this is correct. So Vs is obviously greater than V. This N is less than 1, right? So say it is 0.5. So V is 0.5 times Vs. So Vs is actually higher always.
Okay.
Is it
Okay.
clear?
Yes, sir.
Yeah, N is always less than 1, right? So V is always lesser than Vs. So superficial velocity is always higher than or no velocity. Okay. So this is very conceptual thing. I hope this is clear. Huh? Next we have factors affecting hydraulic conductivity. What are the various factors that affect hydraulic conductivity? So first one is the fluid viscosity. It's how thick, means how viscosity, like ketchup. Tomato ketchup is very viscous, right? Water is not that viscous. So can you tell me, if the viscosity is high, what will be the how will be the hydraulic conduct, how will be the permeability? It will be high or low? If it's more viscous, obviously our permeability will, or the hydraulic conductivity will be low, right? Because it will take, the velocity will be low. So if it's viscous, more viscous, the fluid will take time to flow, right? Similar relation comes with temperature. Okay, so these are the various factors that are affecting our hydraulic conductivity. The temperature, we have pore size distribution. Okay, if the sizes are big size, then this one hydraulic conductivity will be higher. The resistor permeability will be higher. Okay, then if the void ratio is more, means more number of voids, means it will be higher. And roughness of mineral bodies, how much rough it is rough, the mineral surfaces are rough, then it will be lower. Okay, the hydraulic conductivity or the permeability will be lower. Degree of saturation, if the soil is more saturated, okay, then the permeability or the hydraulic conductivity will be higher, right? So these are if we I suggest you go to any under textbook like Gopal, Ranjan and Rao. Everything is very nicely explained in everything, all these books. So I suggest you give just a one reading. Everything will be clear to you. Okay, so now let us start the problem. Just before we start, give me just 1 minute. So let us look into the first problem. So the first problem says that the compaction of a floor area is carried out in 250 thick layers. So in 250 thick layers, the thickness of each layer is 250 The compaction of a floor area, means floor area is carried out. The hammer used for compaction has the foot area of point. The hammer has been used. The like this, some hammer maybe have been used. So the hammer has been used. The hammer has been used. The area of floor area of this hammer is 0.05 meter square. Okay. The energy developed per drop of the hammer is 50 kg meter. It's given to you. For each drop of the hammer, what is the energy? Assume 35% more energy in each pass over the compacted area due to overlap. Means one place maybe we will be doing 2 times or 3 times. It might happen, right, during the compaction process. So due to the overlap, 35% more energy is passed in each pass. So you need to calculate the number of passes required to uh, develop compactive energy equivalent to IS heavy compaction for each layer. Okay, so let us calculate the number of passes required for each layer. So as per our IS heavy compaction, the energy as per IS heavy compaction is equal to 4.9. This is kg force into 0.45 meter. This is actually the drop of the hammer, right? So highest. So I told you before that IS heavy compaction is almost similar to the modified Proctor test. So if you remember the values, you can easily relate these numbers. So 0.49 is the weight of the hammer. Okay, 4.9 kg is the weight of the hammer. For 4.45 meter is actually the drop of the hammer. Okay, into 5 layers. Total number of layers are 5. Okay, into how many layers per blow? How many blows that we give per layer in the compaction test?
25 layers.
Yeah, so, yeah,
25.
correct. So 25 blows divided by, say, this is the volume of the mold, which is 1000 cc for ISC. If you remember, for modified Proctor test, it was the 944 cc, right? Yeah,
Yes,
but
sir.
for IS, Indian standard heavy compaction, it's 1000 cc. It's taken. So 1000 cc into 10 to the power minus 6, it comes into meter cube. So if you do this calculation, compactive energy will come out as 27562.5 kg force meter per meter cube. Now, this is the compactive energy as per my IS, this one, heavy compaction. Now, compactive energy, let us calculate the compactive energy per drop provided by Ramer per meter cube of soil. Okay, so the Ramer that we are using, let us see how much energy per drop that Ramer actually provides us. It is nothing but equal to 50, because the force is given to us that each drop there is 50 kg meter of force. Okay, so 50 divided by the volume. So 250 mm is the thickness, 0.05 is the area of the RMR. Okay, minus 3 into, we will get 4000 kg force per meter. Okay, so this much force per meter cube is generated by the RMR. Okay, RMR in one pass. Or okay, and this much is the compactive effort from the heavy compaction test. Now what we need to do is that we need to compact our soil using this RMR, so that this compactive energy that we are providing matches with that of the IS heavy compaction test. So what we will do is we will just equate it. So n is the number of passes into, and one more thing, it is written that 35% more is uh, passed, right, in each pass. So 1.35 into 4000 is equal to 27562.5. If we calculate n from here, what will it be? 27562.5 divided by 1.35 into approximately 5.1. Okay, so you can do 6 passes. Okay, so if you do 6 passes, then 6 passes using our RMR, then that will be equal to the more than the energy obtained from the heavy IS heavy compaction. Now let us see this. This is the main important problem. These are the main important problems. So the following results were obtained from an IS light compaction test on sample of soil. Okay, following results were obtained from an IS light compaction test on sample. So our light compaction test, which is similar, not same, exactly same, but almost similar to the Proctor test, standard Proctor test, was done, and these were the results obtained. Okay, so we have some values of water content, and corresponding to these water contents, we have the mass of the moist soil. Okay, that was fit inside the mold. Okay, that was actually being able to occupy inside the mold. What we need to do is that we need to plot the compaction curve, obtain the optimum moisture content and maximum dry density. Also, we need to calculate degree of saturation and theoretical maximum dry density. Okay, so let us do step by step. So first we have the water content, right? Water content, let us write 0.12 This is the moist mass. Okay, sorry. Okay. Now, okay, what are the two things that are needed to obtain the compaction curve?
Water plus
What are the two things that you need? What are the two parameters that you need to plot the compaction curve?
density plus water.
Yeah, we need the dry density. What kind of density? Dry density, right?
Dry, okay.
We need the dry density and the water.
Water.
We need these two parameters. Okay, so we have the water content. We have the moist mass, right? Can we calculate the moist unit weight? Can we calculate?
Moist unit weight.
Or moist density? See, mass it's already given, right?
Yes, sir.
What do you need? You need volume. If we divide mass, if we divide by volume, we will get that density.
Yes, sir.
So what is the volume? What is the volume for IS light compaction test?
1000.
1000. So 1.65 divided by 1000. Okay, not 1.65.
Divided by 1000. 0.001.
No. See, 1000 watt, 1000 cc.
1000 cc.
Mean 1 meter cube, right?
Yes, sir.
So in kg per meter cube, if you need to find out, see in kg per meter cube, if you need to find out, just you need to divide by 1. Right?
Yes.
So it will be nothing but 1.65, 1.95,
1.93, 1.90, 1.86.
right? Just a second now. Not kg per meter cube. This is actually in this one, gram per cc. Okay. Okay. So this much. So 1.65 is in kg, right? So that means
Yes.
1650 gram. 1650 gram divided by 1000 your 1000 cc is the volume, so it's 1.65. Okay, so we get the moist unit weight in gram per cc, right?
Yes.
Now from moist unit weight, how can we determine the dry density?
Moist minus water content.
No, remember, try to remember, we have used that term many times, formula many times.
Dry
Relation
density.
dry density equal to some relation was there.
Volume of solid by volume.
Yeah, that is true. But from here, how will we determine? Weight of solid by total volume, that is, you are right. But here, how will we determine? See, you remember this, right?
Yes, sir.
Yes. So we'll use this relation. That is, my density, dry density is equal to the normal or the moist density divided by 1 plus water content. So please find out my dry density here. Please calculate what will be the dry densities. 1.65 divided by 1 plus 0.12.
1.47.
Yeah. Next one. 1.95. Please calculate.
1.69.
Yeah, correct. So like this, you can calculate. Okay. Okay. Like this, you can now can you plot the compaction curve?
Yes, sir.
You have the data, right? You have all the available data. You have the dry density, and you also have the water content. You can easily plot the compaction curve. Okay.
Yes.
Now we'll see that. Okay. Now let us see. When another thing is asked to you. It is asked, calculate degree of saturation and theoretical maximum dry density. Okay. So if you remember, one relation is there. Gamma dry is equal to G 1 plus E, right? Remember this?
Yes, sir.
From here, we can write void ratio is equal to G comma W by T minus 1. Okay.
Okay. Okay, sir.
Right? So from here, we can determine the void ratios for all the cases because G we know. Okay. G you can take. Okay. In the question, I forgot to give G you can take. Take G equal to 2.6. So G you know,
Yes, sir.
gamma W you know, gamma D is equal to, you know. So E you can calculate for everything. So please tell me what will be the void ratio for the first here. What will be the void ratio? Two 2.68 into, remember it's in gram per cc, na? Remember everything.
Yes.
What will it be? 2.68 into 1 divided by 1.47 minus 1. Right? It will be 0.82. Okay, like this you can get, or I will just write. Okay, like this you can obtain all the void ratios. Now this also asks calculate degree of saturation. Now what is the relation for degree of saturation? S is equal to W G by E. Correct?
Yes, sir.
So if you put all the E, W, G and E values, you can calculate the degree of saturation. So it should be nothing but 0.39, 0.69, 0.80, 0.804, and 0.81. Okay, like this you can calculate the degree of saturation. Now, it's also asked in the question, calculate the theoretical maximum dry density. So when will we get the theoretical maximum dry density? When our degree of saturation is equal to 1. So our formula for degree of our dry density is, I think, this. Okay, this we can also write by WGS by S, right? Right?
Yes, sir.
So for theoretical, this is equal to 1. So my formula for relation will be GS gamma W by 1 plus WGS, right? So now please
sir.
put the values. If we put the values here, so please tell me what will be the theoretical maximum dry density for at least for the first this water content you tell. Gamma D max using this relation. Just put the values of G, gamma W1 plus then W and GS. G. This G suffix. Okay, saturation. Please tell me G is 2.68, right? 2.68
Yes, sir. 2.68
into 1 divided by 1 plus
1 plus
0.12 into 2.68.
0.68.
It's 2.03. So similarly, you can get all other values. Okay, so
Yes,
you
sir.
see that theoretically the dry density that is possible are these values, right? Theoretically, these are the maximum possible values. But what you obtained? You obtained only this much, always less than the theoretical value, right? Always less than the theoretical. Okay. So this is actually the graph. So this side, this is my water content, and this side it is my dry density.
Dry density.
Okay, this is gram per cc. So if you plot, you'll get a bell curve like this. From this bell curve, the maximum point, if you take somewhat like this, it will be. So it will be little more than 1 point, like almost, like it will be here almost 1.7, like less than 1.7, almost equal to 1.7. So we need to calculate that from the graph. At this point is my OMC, my maximum dry density. Now let us see the next problem. Same problem, exactly same problem. So water content is given, and also bulk unit weight is given, right? So you need to determine the plot the compaction curve and determine the maximum rate. I hope we can do this. It's exactly the same. So you have all the water content. I will just write here only. So using my same formula, which is equal to gamma d is equal to gamma w by 1, gamma not total, gamma s, gamma total, so total into 1 plus w. Using that, you can calculate the gamma d's, high densities 10.9, 3, 7, 4. Okay, so just say, exactly say same to that. You just plot your graph, you will get something. Okay, from this graph you can find out the OMC and your maximum dry density. Okay,
Yes,
exactly
sir.
same like the previous one, huh?
Yes, sir.
Okay, this calculation of degree of saturation you can do as a homework. Okay, you can do it by yourself. Exactly same like the previous. You can calculate a degree of saturation. Okay, so here they have asked that calculate the degree of saturation at the maximum dry density only. Okay, so at the max from this graph we can find the maximum dry density is calculated as approximately 18.4 kilonewton per meter cube. Okay, so it is asked to calculate the degree of saturation at that percent. Okay, the degree of saturation you can find out using this relation. But yes, so this you know, this you just calculated from the graph is 18.4. 18.4, this you know, G you take as 2.68. This you know, 9.81. This you know, this is nothing but your OMC. This you again you know, so this you can find out. Okay, so this comes, okay, so this you calculate how much it comes out. I'm not calculating. Understood or not?
Yes,
This
sir.
everything you know, just put the values of maximum dry density of your moisture content and you find out the saturation quantity. Now also it is asked that plot the zero air void line. So to plot the zero air void line, what we need to do is that you just need the relation of the zero air void line. What is the, this was already discussed, like G. So this is the relation of the zero air void line, right? For say this theoretically maximum possible value of dry density. Okay, so you just take some values of water content, say 5%, 6%, 10%, like some values you take, you will get some values of dry density. Then you plot the points, you will get a line like this. So this is my zero air void line. Okay. Okay. Very simple, nothing. Just you need to put the values in the relation. For some water content, you will get the values of this. So you got the water contents, you got the values of density, just plot the points, you will get the our zero air voids. So let us go to the next problem. The maximum dye density of a sample by the standard compaction test is this much at an OMC of this much. Find the air voids and degree of saturation. Degree of saturation if G is equal to 2.68. So we need to find out the percentage of air voids. Okay, this this one you need to find out, and also you need to find out the saturation. Correct. So our OMC is given as 14.5%, and our maximum dye density is given at 1.76 gram per cc. Right. So actually there is a direct relation between dye density and my dye density and this percentage air voids, which is nothing but 1 minus Na by 100. Right. So please remember this relation. This is the relation between dry density and your percentage air Na. Okay, so this you know, 1.76 equal to 1 minus Na by 100, 2.68 into 1 by 1 plus 0.145 into 2.68. 0.145 because W is 14.5%, right? So 0.145. So if you solve this from here, you will get your Na is equal to 0.088 or 8.8%. Okay, now it is asked what is the theoretical MDT at this OMC, means at that optimum moisture content, what is the theoretically possible maximum value of the dye density? Can you tell me the relation formula for the maximum theoretical dye density? What is the formula for relation for dye density? Please see the previous things and tell me what is the relation for dye density? What is the formula for dye density?
GS
Hmm?
GS
Then
gamma
now
W
W
divided by 1 plus C.
1 plus E, right? So this E we can replace by WGS by S, right?
Yes, sir. Yes, sir.
Right. So when will we get the theoretical maximum? Theoretical maximum is when we already discussed this 100 times, that theoretical maximum will get when S equal to 1. So S theoretically maximum will be nothing but GS comma W
By 1 plus W
plus
GS.
this one. So please put all the values and tell me what is the answer. 2.68 into 1 gram per cc 1 plus, tell me.
Sir, water content
Water content is your optimum moisture content. Yeah.
up to much 14.
Yeah, means 0.145, right? 0.145, 14.1, 68 will be the answer.
$1.93.
Yeah. Unit
Uh, G by cc.
Gram per cc. Correct.
Gram per cc.
So this is my theoretical maximum. But what was my maximum dye density that we obtained? It was 1.76, right?
Yes, sir.
This is the obtained. And my theoretically what I can obtain the maximum is 1.9.
1.93.
Let us look into the next problem. As per compaction specification in a highway specification, a highway field has to be compacted to 90% of Indian standard light compaction test dye density. Okay, so 90% of the Indian standard light compaction dye density we need to compact a highway. Okay, a borrow pit available near the project site has a dye density of 1.78 gram per cc at 100% compaction and a void ratio of 0.63. Compute the volume of borrow material needed to construct a highway field of height 5 meter and length 1.5 meter with side slope of 1.1:2. The top width of the field is 10.5 meter. Okay, and G is given as 2.7. My dry density from borrow pit, maximum dry density from borrow pit is given as 1.78 gram per cc, and my void ratio from borrow pit is given as 0.63. Okay. Okay. So
Yes,
this
sir.
is my maximum dry density on the borrow pit. Now what is given is that this dry density is actually we obtain it. See these right. So this right. So what we did was that we took soil from the borrow pit and did the Indian light standard light compaction test. And after doing that Indian light standard light compaction test, we found out that the dry density of that soil, which we borrowed from the borrow pit, means the soil which we borrowed from the borrow pit is the 1.78. So there is a borrow pit. From the borrow pit, we took some representative soil. From there, we took some sample to the lab. In the lab, we did the Indian standard light compaction test. And from that test, we found out that the dry density, maximum dry density is 1.78 gram per cc. Okay. Also, the void ratio is given. So this dry density, which you are calling 100% compaction. Okay. So this is the maximum dye density that we can obtain by doing the Indian standard light compaction test. So now it is told that 90% of this dye density has to be achieved in the field. Okay. So this dye density, this field is 90% of 1.78 gram per cc, which is nothing but 1.602 gram per cc. Okay. This much is clear.
Yes, sir.
Now the cross section of the embankment is given. The top width is 10.5 meter and the side slopes are. So these slides, all sides, two side slope are 1:2. Okay. So can you tell me this width from this data? Okay. Also one more thing is given. This height is given 5 meters. So from these data, can you tell me this base width?
Well,
See, this slope is given, right?
yes, sir.
So from this slope, we can know this distance. 1:2 means 1 vertical is to 2 horizontal. Okay. So if you write 1/2, you can write 5 by this distance from here to here. From here to here, say I call it x distance. Okay. By x, so x will be is equal to 10. Similarly, this is also x. This is also x. Okay. 10. So what is the base width? Base width is nothing but 10.5 plus 2 into 10 is equal to 30.5 meter. Understood?
Yes, sir.
Clear na?
Yes, sir. Clear.
How to calculate? The slope is given, and from the slope we just find out the base. Okay, 30.5. Now you know the top width, you know the base width. You can find out the volume. Okay, volume length is also given. You can find out the volume. How can we find out the volume? Volume will be nothing but what is the area of trapezium? Half into sum of parallel sides into height. This is the area, right? And into 1.5 is the volume. Correct?
Yes, sir.
It should be 1.5 km, I think. It should be 1.5 km. So it's 1500. 1.5 into 1000. So my volume comes out to be 153750 meter cube. Okay.
Okay, sir.
Now I have the volume, and I also need the amount dry density that I need to achieve in that volume. Now, what is the formula for my dry density? GD fill is equal to G by 1 plus E fill. Okay, from here this you know, this is nothing but 2.7, this is 1, this you know from here 90%, this is 1.602, this is 1.602. So from here we can calculate the void ratio of the fill, okay, which is nothing but 0.685. Now if you remember from the first lecture, first week, the borrow pit problems. In the borrow pit problems, I had told you that the volume of solids, okay, the volume of solids always remain constant, right? In the both in the borrow pit and also in the soil, in the where we have brought the solid. Means the volume of solids will always be constant, right? That amount of solids you are bringing from here to here. So the volume of solids will also always be constant. So we can write volume of borrow pit by 1 plus E borrow equal to volume of fill by 1 plus E fill. Okay, because my volume of solids is constant. From here, I can write volume of borrow is equal to 1 plus borrow by 1 plus E fill into. So you know all the values. What is one E borrow pit? E borrow. E borrow is what? Nothing but 0.63. And this is 0.685. You calculated. And this volume of fill also you calculate to 153750. So if you calculate, you can calculate the amount of volume of soil that you need to carry from the borrow pit. Okay, so you calculated this as 57486. Okay, so this much amount of soil you need to carry from the borrow pit to your site. Okay.
Yes, sir.
So next question is that in India standard light compaction test, bulk unit weight of soil sample was found to be this much at a moisture content of this much. So bulk unit is given and moisture content is given. What can we find out?
Dry density.
Yeah, dry unit weight you can find out easily, right? So we can easily find out. So that is given, determine the degree of saturation and the additional moisture content that is required for full saturation. Okay.
Okay. Yes, sir.
Let us solve. So first you need to find the degree of saturation. So first thing is that the degree of saturation. So we need this total unit is given by G into 1 plus W, 1 plus W G by S to comma W. Okay, these are all our known relations, right? So total unit is given as 18, G is 2.68, 1 plus 0.13, 1 plus 0.13 into 2.68 by S into 9.81. Correct?
Yes, sir.
If we solve it from here, we can easily find out saturation, degree of saturation. So degree of saturation actually comes out to 0.5356, which is nothing but 53.56%. Okay. So first person, this one, first portion we solved it. Just a second. Now let us find out the void ratio at this saturation. So it is nothing but E is equal to WG by S. So W you know 0.1368 by 0.5356 we do, E will come out to 0.65. So this is the void ratio at this state. You already find out. Now the main conceptual thing comes. Always remember that at any given compactive effort, the void ratio will always remain at any given compactive effort. The E remains constant always. Okay, the E always remains constant. Okay, so now we know that S WG by E, we know this relation, right? Now for full saturation means when S is equal to 1, okay, we can find out the water content. Okay, what we do is that W is equal to SE by G, nothing but 1 full saturation into E, what we already found out 0.65 by 2.68. This comes out to 0.242 or 24.2%. Correct. So initially what we found out our degree of saturation for our soil, which was this much, and also we found out the void ratio at this state. Correct. Void ratio at this state. Now we always remember that for a given compactive effort, for a one kind of test for where you have the compactive effort remains same, for that compactive effort the void ratio is always same. Void ratio is not changing, right? Void ratio is always same. So using that void ratio, what happens, what I'm saying is that here is soil, water. Okay, so initially you compacted something and say you reduce the volume here. Okay, some air was eliminated. Okay, so in this state some percentage saturation is there, which is this 53.56% of saturation in this situation. Now it has been asked to ask if 100% saturation is to be maintained, means all voids are to be filled with water, the remaining voids are to be filled with water, then how much water content uh, extra we do. So what we do is that we put saturation equal to 1 and remain the water content. Very simple. So additional that will be required was that initially it was 24.2. So we need 24.2 and we already have 13. We already have 13%. So additionally 11.2% of water we need to add so that our soil is completely healthy. Okay. So this is not actually that much related to uh, compaction also, this problem. Okay, so if so that's the bulk unit weight is given, the moisture content is given, so from there you find out the saturation of the soil, from saturation we found out the void ratio. Okay, then we find out for perfect saturation means 100% saturation what is the water content, and we just deducted that, found out the additional amount of water. So this is very simple, nothing that not don't confuse this is not that much related to compaction. So the next the in situ void ratio of a granular soil deposit is 0.59. The void ratio in loosest and densest state where this one is find the relative density. Okay, relative density and relative compaction. Two things we need to find out. Okay, now can you tell me the formula for relative density again? What is the formula for relative density? Emax minus E natural by E max minus E min, right? Right? So what is our E max? E max means losest state, right? So what is the density losest state? 0.81 minus natural relative density 59 into 0.81 minus 0.37 into 100. So we get a relative density as 50%. Now, what is my maximum? See, relative density you already find out. Now you have to find out the relative compaction. What is relative compaction? Relative compaction is nothing but gamma d in situ by gamma d max. Okay. So what is my gamma d max? My gamma d max, nothing but E mean, right? When the void ratio will be minimum, only then my density will be maximum. So using this, you can find out the maximum density. This is 37 by 19.33. Okay. So and what is my gamma d in situ? 0.59 is given. So 2.7 into 9.821 into 1 plus 0.59. We get it as 16.65. So what is my relative compaction? Gamma d in situ is 16.65 by maximum 33 into 100%. We will get 86.13%. Okay. See, it's already time. Just guys, 3 problems here regarding this our this permeability chapter. So let us just complete them very fast. Okay. So for in this problem, we see that for the soil specimens shown in figure, calculate the soil permeability if rate of flow is 2 centimeter cube per minute. So Q is given to us, 2 centimeter cube per minute. The area of soil specimen is 8 centimeter square. Okay. So this area is actually given to you, which is nothing but 8 centimeter square. Okay. So you need to find out the soil permeability. Okay. So relation, what is the relation? Q is equal to KIA, right? So what will be my permeability? K Q by I into A. Right. So what is my Q value here? What is my I value here? I is my hydraulic gradient. I is my head loss by length. So what is the head loss here? 15 centimeter minus 5 centimeter if you see from the figure. And over what length is my head loss happening? My head loss is happening over 12 centimeter length. Okay, right? So I will write here 12. Okay, so 15 minus 5 by 12, our hydraulic gradient is 10 by 12, right? 10 by 12. Now from this, in this relation, if I put my Q is nothing but 2 cc per minute, right? So 2 divided by 10 by 12 into 8. So it comes out to be 10 by 12 into 8 is 0.3 centimeter per minute. Okay, this way we found, so the soil permeability is 0.3 centimeter per minute. Okay, so in the next question, it is given that find the coefficient of permeability of a soil which has a height of 6 centimeters. So the height of the soil is 6 centimeter, and this cross section is 50 centimeters square. Water equal to 450 ml passes through the soil in 10 minutes. Means our volume is flow is given. So 450 ml by 10 minutes. Okay, flow by time it will give by volume. Okay, it is nothing but 0.75 centimeter cube per second. Right. So 450, your 450 ml, 450 ml, if you multiply, yeah, 450 ml in 10 minutes is nothing but 0.75 centimeter cube per second. Okay. Now, so what is my hydraulic gradient here? Hydraulic gradient. See, flows under effective constant head of 40 centimeters. So my head is given. So my head is given, which is 40 centimeters. So 40 centimeter by the length of flow is 6 centimeter. Okay, this 6.67 is my hydraulic gradient. So in a head of 40 centimeter, my flow is occurring over a length of 6 centimeter. So I have my hydraulic gradient here, 40 centimeter by 6 centimeter, which is nothing but 6.67 hydraulic. Okay. Now we can calculate the permeability, coefficient of permeability, nothing but same here, same to here, Q by IA. Q is 0.75, I is 6.67 into my area cross section is 50. So the answer is 2.25 into 10 to the power minus 3 centimeter per second. This is the coefficient of permeability. Next, we are also asked to calculate the seepage velocity. So what is the normal velocity? Let me find out. Not this Vs, the velocity. V is equal to K into I. So my K is 2.25 into 10 to the power minus 3 into I is nothing but 6.67. So it is 2.25 into 10 to the power minus 3 into 6.67 is equal to 0.015 centimeter per second. Okay, this is the velocity. Now the oven dry weight assessment is 495 gram. So we need to calculate the see, for seepage velocity we need the porosity, right? We need the value of the porosity. So for the value of porosity we have this. So what will be the dry density? The dry density will be the dry weight by the volume. So what is my dry weight? Just a second. Just a second. Huh? Just a second. Yeah. So what is my dry density?
Dry density
Yeah, so by dry weight was given, right? 495. So 495 divided by volume. Now volume is also known. So 495 divided by volume means area is given to means 50 centimeters square into length 6, right? It will be nothing but 1.65 gram per cc. Now I need to find out, the main task here is to find out the void ratio or the this one n value porosity. So in order to determine that, I know that dry density is equal to G gamma W plus 1 plus C. So G I know, gamma W I know. So from here I can find out E is equal to 0.606. Okay, now what is N? N is nothing but E by 1 plus E. So it will be 0.377. So we have our velocity here, right? Which we calculated. So what will be the seepage velocity? So seepage velocity Vs is nothing but V by N, nothing but 0.015 divided by 0.377 in the 0.377 0.039 centimeter per second. So here you can clearly see that my seepage velocity or the superficial velocity or the seepage velocity is greater than my normal velocity, average velocity, right? Here it was 0.015 and my seepage velocity comes out to 0.039. So it's obviously greater. Okay. So so this problem, this is the last problem. This is actually a very important problem, very conceptual. So today I will explain. Next class, if you don't understand this, next class again we will solve. We will solve again. We will solve a similar kind of problem related to permeability. Similar to this. Okay, same problem related to stratified permeability of stratified layers. We will solve similar to this problem. Okay, so this problem will just help to make the basic concepts of the heads, and then we will solve a similar problem with stratified soils in the next class. So for these are the two cases that are given to you. This is the one first case, the second case. So for each of these cases, we need to determine the pressure head, elevation head, and the pressure head, elevation head, and total head. Okay, at the entry point, exit point, entry, exit, and the A point. Okay, for both the samples. Also, we have to find out what are the superficial velocities and the seepage velocity. Okay, so just to make, this is the seepage velocity and this is my superficial velocity. The seepage velocity is always greater than the superficial velocity. Okay, so this is the thing. For case one, let us see first. So for the case one, so we will just write, okay, the elevation here, we will write elevation point, elevation head, meters, all in meter, pressure head, total head in meters, and head loss in meters. Okay, we have all these things. So for the case one, let us see at 10 elevation means at here. What is the elevation head? It's 10 meters. Above that, no matter is there, right? So pressure head is 0. What is the total head? Is elevation plus pressure head? It is 10. And that head loss is 0. Now for the sixth point, 6 here is the entry point. What is the elevation head? 6. What is the pressure head? 4. Because this height is 4 into the total head. Sum will be the total head is nothing but 10. So head loss is 0. Now at elevation point 2, that is my exit case. Okay, so exit case, what is my elevation head is 2. So what we consider is that during during this flow, all the head will be lost in this portion. So this is what will happen. Okay, so all the head is lost in this process while the water traverses the soil. So while coming from here to here, all the head will be lost. So at the point of elevation 2, so at this point, my head loss complete head loss means my total head should be 0. So my head loss should be 10. Okay. So 0. So what should be my pressure head? Obviously, it should be -2. Then only my total head will be 0. Okay. So this one we got the for point 2. Now for the 0 point. 0 point, what is the elevation? 0. Okay, what is the total head? 0. Then pressure head will be also 0. The head loss will be 10. Now for this point A, let us find out. The elevation is 3, right? 3 for A. What is the elevation head? 3 meter. What is the pressure head? You can see from here to here. Nothing but, sorry, the pressure head you cannot, sorry. See, pressure head you cannot calculate like that. Just a minute. So elevation head you have here 3 at this point. From here to here it's 3 meter. Correct. Now see, now in this length, this 4 meter length, total head loss is 10. Right. What is my hydraulic gradient? 10 by 4. Right. So from here to here, my total head loss is 10. Okay. So let us find out from here to here what will be my head loss, which will be nothing but I into this distance, which is nothing but 3. So 10 by 4 into 3. Right. Nothing but 7.5 meter. So my head loss here is 7.5. Okay. So what should be my total head? If this is so total head should be 2.5, obviously. 10 minus 7.5, 2.5. So what should be my pressure head here? Minus 0.5. So like this, for all the points we filled up this table. Now it has been asked us to calculate the superficial velocity and seepage velocity. See, n is given, porosity is given, k is also given, right? So you just calculate superficial velocity is k into I. This is nothing but my 0.1 into I is nothing but 10 by 4. Okay, whatever it is, this is my superficial velocity, and my this is n v by n, nothing but v by 0.33. Okay, so this will give my seepage velocity. So my main velocity, my superficial velocity will be 0.25 centimeter per second, and it will be 0.25 divided by 0.33, 0.7575 meter per second. Okay. So in the same way, I hope you can calculate for this case 2. I hope you can calculate for case 2. So this one is homework. So you can calculate this, and I will, okay, if we get time, we'll be solving it again. And that time, I hope you will be able to tell me how to solve this problem. Okay, so this is exactly same as case 1, little different. Okay, so this is homework. So I hope you will be able. So this problem was clear, right? So see, for all these points, it's very easy to calculate everything. Just the main point is from for here, for the midpoint, how will you calculate? For A point, how will you calculate? So how do we calculate? We first found out the hydraulic gradient. Okay, for hydraulic gradient, we found out the head loss, and from there we could fill up the update table. Okay, and using this hydraulic gradient, we could also calculate the superficial velocity and the seepage velocity. And also we can again see that the superficial velocity is always greater than the seepage velocity is always greater than the superficial velocity. Okay. Okay. So with this, we will end today's discussion, and see you in the next week.
Okay, sir.
Okay, we'll continue again with this one with permeability, and also we will begin with seepage. Okay, thank you.
Okay, sir. Thanks.